Good morning, everybody. I got to see Project Hail Mary this weekend. It was fantastic. It was a really, really good movie. Highly recommend going into spring break, if you can spring it, to go to the movies. Project Hail Mary is a good one. I say this as a nerd and a scientist. It was a great nerdy scientist movie, but it was also just a good movie. My wife, who is a musician, loved it, right? Good music, good visuals, good story, good acting, just all good puppeteering. Like everything about it was so good. So can highly recommend it. I also highly recommend the book. I believe the book was better, but the movie was a real close second. Usually a movie's like not nearly as good as the book. This one's good. This one's good. So can highly recommend that. This is not Mr. Balogh Goes to the Movie Hour. This is chapter 10. Okay, so some weirdness that's happening, right? We got spring break coming up, right? That's next week. Grasp is happening this Friday, but I assume nobody will be there except me. We have the exam autopsy this Wednesday, right? That'd be a great day, not only do the test autopsy, but I'm trying to do chapter 10 in like one day. I'll get mostly there. But it'd be a great day to do like chapter 10 homework, right? I know everybody doesn't want to stay in physics, but usually the test autopsy takes 45 minutes or so. You got all that extra time. You can sit there and pick my brain and get help on the homework, all that kind of stuff. Like try to get this one out of the way so you can enjoy spring break. Nothing's due spring break, right? Is there something due this Friday? Is chapter not this Friday? It's on Saturday? It wasn't supposed to be. It was supposed to be due Friday. Oh, well. So I guess there is something technically due during spring break. But try to get chapter 10 done before spring break so you don't have to worry about it. And then this unit, keep track on Canvas. We're doing chapter 10, and then we're doing chapter 16, thank you, and 17. So this unit is 10, 16, and 17. I believe that your author made a mistake in the order that they're presenting the information. So the chapters we're skipping we will do as the last unit. So 11, 12, 13, and 14, and 15. Those are all thermodynamics. So if you've had chemistry before, it's going to sound familiar. If you haven't, you won't suffer like the other people have. So that's kind of the rest of the semester in a nutshell, right? Okay. We'll have a test. I can't remember what your fourth test is, but it's like a couple weeks after we get back from spring break. All right. We are doing something new, okay? Which is namely this, okay? What I've got here is a mass on a spring, right? Okay, and we are going to take a look at this motion and try to we know quite a bit of physics right now. I know you feel like you don't, but you do, okay? Kinematics, energy, forces, Newton's laws, all that stuff, right? It's floating in your brain somewhere. We can use all of that to explain what's going on here. This is called simple harmonic motion. Physicists are very rude when we throw words around like simple. What we mean by simple is that we are going to do no friction, okay? And we're just simply going to look at the motion itself. This is quite unique compared to anything else that we've done before, okay? A lot of what we've done before has been something rolling down a hill, a car accelerating, and it's kind of a one-way trip, isn't it? Like something happens, we see what happens, we've got the answer. When it comes to simple harmonic motion, that harmonic in that description means that the motion repeats itself, right? If I pull this down here, right, and I let go, well, first of all, it wants to hang in one position only. So if I just let it be at rest right here, I'm going to draw a line on the board to indicate that this is the equilibrium point of this oscillator. Remember how we used to be able to pick 0? Not anymore. Okay. 0 is the equilibrium position of whatever it is that you're going to have bouncing back and forth. Okay. when I pull this down and let go, okay, I've given it a displacement here, right? Okay, if I let go, right, the displacement is roughly equal top to bottom, okay? And so if I kind of pull it down and I give it a mark right here, okay, and I let it go, and I go up to where it was, then pretty close, I've got it swinging kind of funny, but it's pretty close to being equal top to bottom, right? Okay, this is going to be called amplitude. The distance, maximum distance from equilibrium is referred to as the amplitude. And you might notice when I let go, it'll go up to the top, come back to the bottom, and then repeat that motion over and over and over again. My system here, my true physical system, has friction in it. So you can see that we call this dampening, where it's kind of slowly, the amplitude's dying as time goes on. We're going to deal with systems where we don't have that, right? But can anybody name anything in your life that does this?
Door hinge.
Door hinges don't bounce usually. What? Baby bounce chair? It's so fun to watch babies bounce up and down in those little swingy things, right? Okay. But not everybody runs into a baby bounce chair every day. Suspension in your car? What about your car's engine? Does your car's engine do this? Like, Mr. Bailey, my car does not run on springs. No, but it does turn over. Does it have a system where the pistons are going up and down in a regular motion? Do the wheels on the bus go round and round? No. Is circular motion this? Yes. Okay. Now, I mentioned a little while back when we were talking about toolboxes that simple harmonic motion is the toolbox that physicists will default to whenever we don't know what we're doing. We have no idea what we observe something in the universe. We're like, just treat it like an oscillator, right? The reason being is that the toolbox we are going to develop together is going to have everything in it already solved for us. And so we can just run and apply it. It's actually really, really nifty. We'll get there. My example up here is vertical because that's just the easiest to set up and get a mostly frictionless situation going. The one here on the screen is mounted horizontally. It doesn't matter. Vertical oscillator, horizontal oscillator, any motion from the keeping of time to the running of your car to the buzzy haptics in your phone or your video game controllers, any process that repeats itself over and over and over again is harmonic motion. And we're going to deal with all the kinds that don't have friction in them. Notice that in the screen here, right, they're using x as their displacement. That's what we'll use. I'll sometimes even draw it vertically and say that, well, this is the amplitude, but I pull it down a distance x, right, less than the amplitude. That x is just a displacement from 0, right? And again, it really doesn't matter if it's vertical, horizontal, whatever, okay? So notice in this picture, right, in order to get the spring to do anything, what do you have to do? You got to pull it. You got to apply a force, okay? So we're applying a force to this spring in order to get it to stretch. Springs come in all kinds of different shapes and sizes and stiffnesses and all that kind of stuff, right? This kind of brassy golden one here, it's pretty easy for me to stretch, right? Okay, I can get it nice and elongated. This one's stiffer, right? Takes a little bit more of my shoulder strength, which I don't have right now because of my neck, right? To get that one to stretch. So there is a relationship called Hooke's law, Hookes. And you're going to see this one written several different ways, unfortunately. They all look similar. I wrote it that way for a reason. You'll see it written like this. F equals negative kx. But notice the negative sign is there along with what? The vector directions for what's going on. And then you'll see it written as I've written it up here. Notice this is a magnitude equation. You might even see it written as F equals negative kx without any vector signs on it at all. Okay? The negative sign is misleading because you like to look at equations and think they are gospel truth and they must always be obeyed. This negative sign is a reminder. If I pull down on this spring, which way is the spring pulling? Up, right? I pulled down, but the spring is trying to pull it back up, right? If I push up on this spring, which way is the spring applying a force? It's now applying a force down. What's the minus sign here for?
That it's opposite.
It's a reminder that if you compress a spring, the spring is trying to return to equilibrium. And if you stretch a spring, again, it's trying to pull it back to zero. That's what the minus sign is there for. When you need to calculate the force in a spring, do you use the minus sign? If you just need to know the force that a spring is exerting, do you need the minus sign? No, because force is just a number, right? The direction that that force will be applied will often just be in a diagram, right? So it gets a little bit confusing. Physicists always running around writing F equals minus kx. Engineers write minus kx. And then in the very next line, the minus sign disappears. Again, the minus sign is just a reminder that conceptually, the force that a spring applies is opposite the direction of its compression or stretch, right? It's just kind of always fighting to get back to zero. So that one's called Hooke's law. On this page, this page. So I'm going to try on this screen right here to get down all of the toolbox equations, right? So I'm going to, how am I going to do this? I think what I'm going to do is everything in black is going to be a main toolbox equation. I'm going to need a little bit of scratch work off on the side to just kind of help tell the story. But I'll try to make sure that we get all the main toolbox equations off in black, and I'll box them at the end so that we have the toolbox. It won't be complete. We're going to add something else to it in a little bit, okay? But we need to talk about, again, some of these words that we use when we're talking about simple harmonic motion. We already learned amplitude. Amplitude's the maximum displacement, okay? So we also have what we call period and frequency. Now, we've run into these things before. We ran into period and frequency in the very first lab we did that actually had equipment in it. Do you remember way back at the beginning of the semester when you were little physics babies? And we did the pendulum lab? Learning how to use the computers and stuff like that, okay? Talked about period there a little bit. And I said, don't worry about the 2 pi, it's coming later. Today's the day you worry about the 2 pi, okay? The amount of time it takes for this thing to go up and come back to its starting condition, okay, is the period. So feels like this one's about a second, right? 1 second for it to kind of go up and come back down again, right? If I start it up here and drop it, that's about the same time, isn't it? Okay, so that's a full period right there. So period is the amount of time it takes for it to do one complete oscillation. These are just definitions. The frequency is the inverse of the period. Oops. Those are different F's, by the way. Okay? So capital F, force. X is a distance in meters. Oh, we didn't talk about K. K is the spring constant. It tells you how floppy or stiff your spring is. So the bigger the K, the stiffer the spring, the stronger the spring has to be. So this one has a low K or spring constant. This one has a big one. And what are the units of the spring constant? It's a force divided by a distance. So what's force? Newtons. Distance? Meters, right? So spring constant is newtons per meter. Okay. What are the units for period? Seconds. It's a time. Okay. So what does that mean the units of frequency are? Yeah, it's a 1 over a second, which is also called a hertz. And you've heard of hertz before. You've probably run into a computer sales pitch where they tell you that the processor is running at 5 gigahertz. That hertz right there means per second. So in a computer, so first of all, what does giga mean? It means a billion times 10 to the 9. Okay? So the computer's processor is completing 5 billion computational cycles per second. 5 gigahertz, right? Now, computational cycle is kind of complicated and can mean different things. But if you want to think of it as maybe just like an addition or subtraction, you can. It's a bit of a lie, but it's a good one. So hertz is how we talk about frequency, and that's going to come up later when we start talking about waves and sound. All right, so we got those units. We got that. Okay, there's another one. This one's coming back. It's rejoining the band. The band broke up for a little bit, but now it's back. What's this? Omega. Good job. Didn't say W. I don't have to get mad. Okay. Where did we first encounter omega? It's angular velocity, right? You remember the units of omega back then? Radian per second, right? What are the units of omega here? It's a radian per second, right? Because frequency is a hertz, and a hertz is a 1 over a second. And 2 pi has units of, well, non-units of radians, right? What's omega? I lied to you back in circular motion. Yeah. Oh, I lie all the time. You do not want me to tell the truth when physics is concerned. Okay? Because if I told you the truth, you'd all quit. You'd run screaming from the room, right? You do not want to have to do the mathematics I had to do in college. I promise you. Okay? So, what was the lie? Or maybe not so much a lie, but a misdirection. I told you omega was angular velocity. Actually isn't. It's angular frequency. But angular frequency and angular velocity are the same thing, right? It's not so much how fast something's going, but it's an angular version of the frequency. How often does something repeat its motion? Okay, so I'll refer. I had to try really, really hard back in chapter, what was that, 8, to not slip. Like I had to concentrate and refer to omega as angular velocity, because what I wanted to say is that it was angular frequency. So it's back. Okay, so we got that. All right. Here's part of the issue. Okay, the force that's acting on this mass as it bounces back and forth, the force that causes the harmonic motion is Hooke's law, kx, right? Okay, but we also know that the force, a la Newton's second law, is mass times acceleration, right? And we know the mass. So if we solve this for acceleration, we get negative k over m times x. There's a problem with this equation, and it's not physics and it's not math. Does anybody see the problem? It's very subtle. No? When we were doing, let's just do kinematics, okay? Wrote down all that toolbox. We made an assumption about the acceleration. It was constant, meaning it never changed, right? Slam on the brakes, whatever the acceleration is, it's the acceleration the entire time the car is stopping. When we did Newton's laws, again, the acceleration was constant. When we did energy, we didn't talk about acceleration because we didn't have to. When we did circular motion, right? Anything that was speeding up or slowing down kept the same amount of speed up and slow down. Is the acceleration constant anymore? K is a constant, M is a constant, but X is a variable, right? So what this means is the acceleration changes at every point along the motion. Where is the acceleration the smallest, or 0? At equilibrium. When x equals 0, what is the acceleration? 0. So where is the acceleration the biggest? At amplitude, because amplitude is the biggest x ever gets, right? So what we have here is an acceleration that goes from 0 at the middle to its biggest values at the ends, and is whatever it is in between. Unfortunately, or fortunately, depending on where you look at it, this requires calculus to figure out. To be able to write down a toolbox of equations for the oscillator, we actually have to solve this is a differential equation. Okay? Some of you have to take calculus. You have to take, was it 5A, 5B? Do you have to take Math 6? No? Yes, some of you. Depends on your majors. Okay? So differential equations crop up in Math 17. Okay? Right? They're a step above. They're a type of calculus, right? But they allow you to solve equations that have derivatives in them, as well as this. Acceleration is the second derivative of position. We're not going to do any of that. We are safe from that. What I'm instead going to do is I'm just going to regurgitate a bunch of equations that are consequences of all the stuff I'm going to lie to you about and say you don't have to worry about. Okay? You don't have to worry about the math. You do have to worry about the consequences. Okay? So here's one of the consequences that comes out of actually solving some of this stuff. The maximum velocity that this mass on a spring will ever achieve, anything that's going in harmonic motion, is equal to omega times a. I think your book did it the other way, a times omega, but it doesn't matter. Okay? So again, coming out of nowhere for you because we didn't do any of the calculus, but you can derive the fastest speed that this thing will have. You can also derive the most acceleration this thing will have, which is going to be omega squared times a. Your book, I don't think your book doesn't, it might have it in it, but it doesn't highlight it. You can actually get the position as a function of time of an oscillator using that, or, and it actually doesn't matter if you sine or cosine, that. Because in essence, what is this thing doing? It's oscillating just like sine and cosine functions do. Okay? I'm not going to really hold you to that too much. Again, your book doesn't highlight it, but just realize that behind the scenes there's lurking sine and cosine wiggles. Okay? Not our right triangle sines and cosines that we've always been using, right? But the actual function that wiggles up and down. You can actually use it to predict where things are going to be and all that kind of stuff. Okay? So I dropped that in there because ChatGPT, AIs, other websites, they'll say, oh, but the thing is, and the reason you use sine or cosine just depends on where you start it. If I start it down here or up here, so my time 0, it's at amplitude. What's the cosine of 0? 1, right? So with cosine of 0, I'm at amplitude, right? It starts at amplitude. When would you use sine? If it starts at its equilibrium position. Like at its equilibrium position, let's say I push it up, right? Then you would use sine. So that's the difference between using sine and cosine. It depends on what we call the initial condition of the oscillator. But I shouldn't have written that one in black. I can't change the ink, so I'm just going to stick it way over here in the corner. Okay? It's part of the toolbox, but not one that you will need to worry about too much. There's going to be more here, but let's just pause real quick. We already talked about where the acceleration is the biggest, right? Acceleration of an object that's undergoing simple harmonic motion is always biggest at the amplitudes, at the ends. It's where it's turning around, right? It's going from one direction to another direction of velocity. Where is the velocity the biggest? Where in the motion do you get V max? At amplitude? What's it doing when it gets to amplitude? It's turning around. So what's its speed when it turns around? It's 0, right? It's going one way. It has to stop to be able to come back the other way. So speed is at a minimum when acceleration is at a maximum. So if acceleration is 0 in the middle, where do you think V max happens to be? In the middle. Another way to think about this is the middle is the only place where the mass isn't being pushed or pulled on, right? Everywhere else it's being pulled or pushed on, meaning it's slowing down. And why is it slowing down? What does the spring always do? Act against the direction of compression, right? So there's a lot of concept floating around behind these equations. I mean, not terribly hard to calculate with, right? Find omega, find the amplitude, we're done, okay? This toolbox looks a little bit simpler. It's going to get more complicated here in a minute. This toolbox is different, though, from the toolboxes we've had before, because this toolbox has a key. So the kinematic equations, that toolbox was open. You could steal the tools whenever you wanted, okay? But there's something that is appearing in pretty much every equation. What's the most common symbol in the toolbox? It's omega. Omega is the key to this toolbox. Find omega whatever way you can, and then the toolbox opens up and you can do whatever you need to do. The difficulty in simple harmonic motion often comes down to finding omega. Find omega, you're home free. One way to find omega is take the square root of the spring constant divided by the mass of the object that's bouncing back and forth. Okay? So I'll box this for now. We're going to add to it, okay? But we got to do some other things before we start adding to it. Again, what are the units of omega? It's a radian per second. Okay. And just while we're here, units of V? Meters per second. Units of acceleration? Meters per second squared. That's all the same, right? The new unit up here, I think, is probably hertz. We haven't encountered that in this class yet. Okay. So let's do a bungee jumper. Okay. So a bungee jump is a bungee jumper simple harmonic motion. Kind of, right? So if this bungee jumper starts up here at the tower, top of the tower, right, and then jumps, right? All the while that bungee jumper is falling and has not reached the equilibrium point of the bungee cord, what kind of motion are they doing? Free fall. Because the bungee cord is not stretching or compressing. Gravity is acting on the person. And when gravity is the only force acting on an object, we call that free fall, right? It's only when the stretch begins, right, that we start getting the harmonic motion, right? Now, a bungee cord is not like a spring. A bungee cord can't push, right? You can only put tension on the bungee cord and have it pull back, but as soon as you try to compress the bungee cord, it just flops around, right? So we're not going to get a full period out of this bungee cord because the person's going to come down, it's going to stretch, they're going to come to a stop. Why are they going to come to a stop? Force of the bungee cord, acceleration is max, speed is 0, right? We've reached amplitude. And once we reach amplitude, what happens now? It goes back up. And once the bungee jumper reaches equilibrium, the bungee cord can't do anything anymore. So what is it going to be? Free fall until it starts stretching again, goes to amplitude. So it's like the bungee cord does a half period and then free fall and then half period and then free fall and then half period over and over and over again, right? And then they put dampeners in bungee cables so you don't sit there and bounce up. I've never done bungee jumping. I have done mountain climbing where I inadvertently became a bungee jumper, sort of. Climbing ropes are not as bouncy as bungee cord. Okay, and yes, it hurts when you fall. Okay, even if you don't hit anything, when you hit the rock on the way down, it hurts too. But yeah, the climbing ropes do elongate and stretch out, but it still feels like you've hit a wall. Anyway, I think the furthest fall I took in climbing was about 30 feet. About 30 feet. I recommend climbing. I don't recommend falling. All right. So, how are we going to do this? How do we start any problem? New toolbox or no? We visualize. We write stuff down. We organize our information, right? So, I'm going to kind of draw a platform, a bungee jumper, woo, right? And then like this is the equilibrium position of the bungee cable, right? And they're gonna end up dangling from their bungee cord, something like this, right? Okay. I like to start with the end in mind. Like, I kind of like to know where we're going. What's the question asking me to find?
How long does it take?
How long, right? So we're going for some sort of time, right? Okay. And the time, sort of by implication here, is from when it begins to stretch, like from equilibrium to amplitude, and then come back, right? It says return. So I'm going to interpret the question as the stopwatch starts there, bungee jumper comes down, bounces back up, and returns to the equilibrium position. So they just want to know how long they're going to be stretching the bungee cable, the amount of time it takes. Well, how am I going to find that time? Kind of already said what we're going to do. While this thing is being stretched down here, can I use kinematics?
Yes.
No. Why can't I use kinematics here? Because the acceleration is changing, right? Okay. Can I use conservation of energy? Can I use circular motion? I have to use simple harmonic motion in this section right here. This is the simple harmonic motion section, right? So I've got to use that. And in my toolbox, I've got things like period and frequency and velocities and omegas and all that kind of stuff, right? Okay. So is there a way that where's time sitting in this toolbox? It's sitting in the period, isn't it? Period and frequency. So I'll get rid of these slides. So the time is going to be related somehow to my period, right? In fact, it's going to be half of my period. Why half? Right? A full period would be down all the way up to the other amplitude and then back down to the middle. Here we're just doing down and back up again, right? That's only half of the oscillation. So if I can find the period and then divide it by 2, I've got the answer. So how are we going to find the period? What do you need in order to unlock the toolbox? You've got to find omega. Because omega is related to frequency. What's frequency related to? Period, right? So that's kind of my plan of attack. I haven't finished sort of visualizing everything here. So let's see, what else have we got? Not much. We know that the unstretched length of the bungee cord is 20 meters, right? However, when the person just hangs from the end, so like here's the bungee cord and the person's hanging, that person is not being hung. They're just hanging. Anyway. We know that it stretches how far? 5 meters. Okay, how are we going to find omega? But it's like kind of one of the only ways we have to find omega right now. Square root of k over m. Did they give us the mass of the bungee jumper? I think they did, right? Did they give us k? Sort of. Here's an example of reading between the lines. The bungee jumper just hanging from the ends of the bungee cable has a mass, doesn't it? mg, the weight of the bungee jumper. Okay. That's how much force got applied to this bungee cable, which is our spring. What does Hooke's law have to tell us about how much a spring is going to stretch? It tells us all about its spring constant, right? The spring constant is the force divided by the stretch. Well, what's the force here? mg. What's the stretch? 5 meters, right? So we can find our spring constant. Did I write this down? I got 137.2 newtons per meter, right? 70 kilograms times 9.8 divided by the 5 meter stretch. That data that they gave us for just the static hang, not bouncing up and down, of the bungee jumper told us what the spring constant of the bungee cord was. Now that we have that spring constant, can we find omega? Yeah. It's going to be 137.2 divided by 70 square rooted. I got 1.4 radians per second. Now that I know omega, is it possible for me to find what I'm looking for, the period? Do I have any equations that relate omega and period? Omega is related to F, which is related to period, isn't it? So if we're back over here, let me take this line out because we're going to add something. Let's see. F is equal to 1 over the period, right? But it's omega is also equal to 2 pi f, right? So let's see. Omega over 2 pi is equal to f. So if I put these together, omega over 2 pi is equal to 1 over t. Or omega is equal to 2 pi divided by the period. That's just a kind of a freebie you can put together to shortcut omega and period, right? Because frequency and period are related, so is omega and period. So now that we know omega, we can use omega is equal to 2 pi divided by the period. Period is going to be 2 pi divided by omega. That's 2 pi divided by 1.4 radians per second. What are the units of my answer going to be here? Seconds. Why seconds? Because I'm solving for a time and I put standard units in. Okay? So is that my answer? I box that and I go? No. This is the whole period if the bungee cord were a spring and bouncing up and down. We already said that we don't want the full period. What do we want? We want half the period, right? So my time is going to be the period 4.5 seconds over 2, or 2.25 seconds. Yeah.
How did you get 137.2 again?
I did mg over 5. 70 times 9.8 divided by 5. This isn't the only thing we can find. I think time isn't actually of the greatest amount of importance. Like, this is the time it takes to slow down. What would concern me the most is what's the amplitude? Like, if we jump from a tower that's, say, 40 meters tall, right? I got to fall 20 meters with no stretch of the bungee cord, right? How much is the bungee cord going to stretch? Because if it stretches more than 20 meters, it's a bad day, right? So to avoid lawsuits, you make them sign a disclaimer so they can't sue you anyway, right? But is there a way for us to find the amplitude? If we could find something, right, that would help us. So acceleration max, we know that's 0, but 0 equals omega times, that's not going to help us solve anything, right? So that kind of leaves us, about the only other thing that can really help us is this V max equation, right? So do we know the maximum speed that this person is going? Can we find it? Where is this person going the fastest? At equilibrium, right? They are going the fastest when the bungee cord begins to stretch. After that, the bungee cord is going to be slowing you down, right? So this is the fastest they're ever going. Before that, they did 20 meters of free fall. What's V max? It's going to be the square root of 2gh. How did I know it was going to be square root of 2gh? Because that's always the answer. For anything that falls through a height h when there's no friction, conservation of energy just tells you, right? mgh equals 1/2 mv squared, solve for v, square root of 2gh. So I know what the maximum speed for this problem is. This isn't always for all oscillators. But because this bungee jumper was in free fall, I can tell you how fast they were going. This is 19.8 meters per second. And since v max is equal to omega a, that means a is equal to v max over omega, which is 19.8 over 1.4, or 14.1 meters. How high above the ground do you need to make sure this bungee tower is? At least 34 meters above the ground. Hopefully more. 40 would be good. Or 100. Put in a lot of error margin, right? Does this change for the weight of the jumper? Would all of our things change if the mass changes? Yes. Okay, the spring constant probably stays the same for the bungee cord, but the mass of the jumper affects period, acceleration, velocity, all that kind of stuff, while simple harmonic motion is going on, right? So you need to make sure that the bungee cable is good for a range of masses, which is why they say you have to be this tall to ride this ride. And in the case of bungee cabling and skydiving and all that stuff, there's a minimum and a maximum on the weight. All right. So there's more to the toolbox, okay? And so to get more to the toolbox, I have to introduce you to a new kind of potential energy. Last unit, we introduced you to a new kind of kinetic energy, the rotational kinetic energy. Well, now we're going to have a new kind of potential energy. It's called elastic potential energy or spring potential energy. Those terms are interchangeable, okay? But it talks about the amount of energy that is stored in a spring, like when you're just holding it here, right? Why is it going to go up? there's a force, right, in the spring. That force is going to do work. That work is going to be equal to the potential energy that's stored. The short version, since we're kind of moving fast and doing a speed run of chapter 10, the potential energy of a spring, or the potential energy elastic, sometimes PE sub S or PE sub E. I don't like the sub E as much because it starts confusing me with other E's that are around. Okay, but a spring potential energy is 1/2 K x squared. K, the spring constant, X, the amount of stretch or compression. Doesn't matter if X is positive or negative. Why? We're squaring the darn thing, right? What are the units of this potential energy? Joules. It's energy. So it has units of joules. Okay? So the full conservation of energy equation. Work non-conservative is when you've got friction or something else, right? Not gravity, not kinetic energy, and now not springs, because we're going to deal with springs with potential energy. So work non-conservative can be whatever it is, but your final energy can be 1/2 mv squared, 1/2 I omega squared, mgh final, and now 1/2 k x final squared. All of that right there are possibilities for energy final. So with spring potential energy, we have a new question to answer. The questions are, is it moving in a line? Is it rotating? Is it at some height h? And now, is there a spring? Right? Is the spring compressed or stretched at the final position? So we're just adding questions onto this conservation of energy statement, right? And then we subtract off the initial energy. And you ask all the same questions. Is it moving initially? Right? Is it rotating initially? Does it have height initially? And is there a spring that is compressed or stretched initially? Just more things to have. I will never give you all 4 of these at the same time. Do not try to picture a rotating spring. They exist. It's called torsion. But no, right? You probably will have like a spring at the bottom of the hill or the top of the hill that's launching it or something, right? It'll be 2 of these things, right? Okay, let's do a quiz. With this energy equation, we can add some stuff to our toolbox. I'm going to go back here. Where's my toolbox thing here? Okay. And I'm going, yeah, I'll do it here. Yeah, no, you know what? Changing my mind on the fly. I'm going to copy this thing. Ah, that didn't work. Can I copy you? You're going to copy all the right stuff? Oh, good. Okay. I just doubled it. There we go. And then put it all over here. Okay, let's stick it right there. All right. So this is our toolbox from before. I'm bringing it forward because we're just going to add some of the things we know, right, because of our new energy formulation. The potential energy of any spring is 1/2 Ka squared. The maximum energy, or what we're going to call the total energy of any spring, is going to be 1/2 Ka squared. Okay, so what's happened there? What did we put in for x? The amplitude. Remember, the amplitude is the most this thing will ever be at, right? So as this thing bounces up and down, does it ever go past its amplitudes? No. So this thing's, the most energy it ever has is 1/2 Ka squared. That's its total energy. What energy does it have at the amplitude? Let's give it a number so you guys have it easier. Let's say it's 10 joules down here. Okay? How much energy does it have up here? 10 joules. How much energy does it have at equilibrium? 10 joules. Why is it 10 joules? Energy is a conserved quantity. The amount of energy you start with is the amount of energy you end with. So if it has 10 at each of the amplitudes, what does it have at 0? 10. What does it have in between 0 and amplitude? 10. It has 10 everywhere, right? And we can find what that energy, total energy is, if we know the amplitude. Okay? What is happening to the kind of energy you have? Where is the kinetic energy the most? Is it at one of the amplitudes?
No.
Why not? Its velocity is 0 there, isn't it? Right? It's stopped at amplitudes. So what do we know about amplitude? What kind of energy does it have there? It's either all kinetic or all potential. Which one is it? It's all potential because it's not moving, right? Okay? It's like it's at the top or bottom of the hill at this point, right? Okay? It then gains kinetic energy as it moves to its maximum kinetic energy at the equilibrium point. And then what happens to that kinetic energy? Shifts back to potential. And then from potential to kinetic at the center. And then kinetic to potential at the ends. Potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic. Over and over and over again. When it's in between, when it's not fully kinetic and not fully potential, what is it? It's a mix, right? But the total is always going to be whatever we started with. Okay? So we can write down sort of that total energy as 1/2 Ka squared. We can also write it down as 1/2 mv max squared. And if you stick omega A in there, you actually get K squared. And we'll kind of just sort of leave it at that. There are a lot more toolbox equations. They aren't in your book. They're more for the physics 4 students. But simple harmonic motion unlocks a huge toolbox of everything sort of being pre-solved for you. And the trick is just finding omega. And once you find omega, you can do just about anything. So let's do an example of that. Okay? Visualize. We've got a spring connected to an object on a horizontal surface. And it says it's smooth. What is that supposed to mean? No friction. Okay? Okay, so it's pulled from its equilibrium position. Let's call this equilibrium. And it gets pulled off to the side by a force. What's the force? 20 newtons. Okay, and how far is it pulled? 0.2 meters, right? Okay. Not knowing anything else about the problem. Looking at the end and going, oh my gosh, it's asking me to solve everything, right? See how it's listing out stuff? K, F, Vmax, all this different stuff, right? Not knowing anything about where we're going, what's something we could find right now? We have a force and we have a stretch. We can find the spring constant. They gave us a force, right? 20 newtons. How far did it stretch? 0.2 meters. What can we solve for? K. Why would we want K? Because it'll help us find omega. Remember, omega is square root of k over m? And if we know omega, what do we know? Everything. We know everything at that point. So even before I figure out what it is they're asking me to solve for, I'm going to find omega. Okay? So I'm going to use Hooke's law to find my spring constant. That's going to be the force divided by the stretch. The force is 20 newtons. The stretch is 0.2. Did I write any of this down? I got too excited. Nope. Sometimes my notes betray me. I have no idea where they go. Yeah, I don't have any of this. What's 20 divided by 2 is 10 point. So is this 100? Okay. So there's my spring constant. Okay. Now that I know that, I can go ahead and find my omega. I know I'm going to need it. So this is 100 divided by the mass. 2, that's the square root of 50. Radians per second. I don't know what the square root of 50 is. Don't care. So now that I have omega, I can solve for anything. What do you want? You want frequency? I got that. You want period? I got that. Maximum speed? I can find it. Maximum, I can do anything. Anything. What do they want to know? Find K. Done. Find the frequency. Which of these equations do you want to use to find the frequency? Omega equals 2 pi f. So we can solve for the frequency, right? 2 pi f is equal to omega. So that means the frequency is going to be omega divided by 2 pi. That's the square root of 50 over 2 pi. We should probably just find the square root of 50, shouldn't we? Square root of 50 is 7.07. And that divided by 2 pi, I got 1.13. 1.13 what? Hertz. It's a frequency, and I put everything in standard units, so it should come out as hertz. All right, K done, frequency done. Vmax. To find Vmax, what am I going to need? The amplitude. Did they tell me anything about amplitude? Yeah. It happens to be exactly the same number that they told us they stretched it out by. Right? So I know that my amplitude is 0.2 meters. So therefore, Vmax is omega times A, which is 7.07 times 0.2. I got 1.4. And how do I know it's meters per second? What am I solving for? Velocity. And I put in units that were all standard. Radians per second and a meter. It's got to come out as meters per second. Okay? Got Vmax. Amax. Not to be confused with the robot Bmax. Omega squared A. So that's 50 times 0.2. 10. 50 times 2 is 100. Move the decimal, that's 10. Where did the 50 come from? It's omega squared. And what was omega? Square root of 50. Right? So it's squared, right? Did I do that right? 50 times 0.2 is 10? Okay. Sometimes I do it in my head. I'm not sure. Okay. Energy total. What's the most energy this thing's ever going to have? 1/2 Ka squared. Right? So that's 0.5 times K, which was 100. So that's a 50, times my amplitude, which is 0.2 squared. I can't do that anymore in my head. Squared. I got 2. 2 what? Standard units in equals standard units out. What else do you want to know? Its favorite color? Political preferences? Once you know omega, you know everything. It's just a matter of putting the pieces together. Don't have time to talk about it very much. A pendulum is a simple harmonic oscillator. Your book offers a couple of equations. We did one back in lab number 3. The way your book writes this one is 2 pi f equals the square root of g over L. It's one way to do it. This is also 2 pi times the square root of L over g. The mystery of the 2 pi. Like, why is 2 pi floating around kind of everywhere in our toolbox and all that kind of stuff? Springs, pendulums, and circles. They're all the same thing. They all are motions that repeat themselves. And so it should come as no surprise that pi ends up getting involved everywhere in all of this stuff. In this picture up here, do you see how this pendulum, they're sort of mapping the swinging of back and forth of the pendulum on a piece of paper as it rolls by? What does that wiggle look like? A sine or a cosine, doesn't it? And sines or cosines are simple harmonic oscillators, are circles, right? So it kind of comes as very little surprise. There's another interesting sort of thing that they drop on you, okay, from your book, and it's this one. This one is the equation for a, so the top one is the equation for a simple pendulum, a mass hanging on the end of a string where the string has no mass. This bottom box is for a physical pendulum. It would be like a mass that's on a bar, right? And the bar has a moment of inertia I about some axis. I want to give you a reason for simple harmonic motion. I mean, it's everywhere. It's literally everywhere, but sometimes it's hiding behind some very common everyday things. What I want to do is I want to give you a very specific application where understanding simple harmonic motion, specifically the physical pendulum, has added quality of life to our human existence. Does anybody know what gait is? G-A-I-T. It's how you walk. It's a word that describes your natural way of walking. Okay? My natural way of walking, my gait, is determined by the length of my leg bones, the mass of the muscles in my legs, and when everything is working correctly, my gait is natural and smooth. But when the gait alters, there's a problem. And you've probably, I'm going to over-exaggerate this quite a bit, but you've probably seen somebody that kind of like maybe walks a little bit like this. Okay? What's happened? Something's wrong. They're wearing a boot, maybe they're in crutches, maybe they can't bend their knee anymore, or maybe they're an amputee. And they either don't have their prosthetic or their prosthetic has been poorly tuned to their body. A friend of mine in high school had a prosthetic leg. He didn't have his leg from just above the knee, actually. So bottom of the thigh down was missing. And, people made fun of his prosthesis. They mostly in elementary school and stuff like this would make fun of kind of the funny way that he walked, right? Why was his gait incorrect? Where is the pendulum in you? Okay? you're walking and you're swinging, right, a pendulum. It's actually a double pendulum, okay? It also articulates at the knee, right? And everything I'm about to say applies. It's just a lot more complicated for a double pendulum. But you basically have a pendulum that's swinging back and forth. The surface of this table is also tipping, so I need to be careful, right? Okay? So it swings back and forth as you walk, right? Swinging back and forth. My friend who didn't have anything from the knee down, right, but instead had a prosthetic, the frequency of one of his pendulums, one of his legs, was different than the frequency of his other pendulum, which led to that kind of like rolling motion where one leg was moving at a certain frequency and the other leg was moving at a different frequency. When he was about 16, 17, kind of had his full growth on him, he came to school one day. He always wore pants. And he was just trucking along, right? And you couldn't tell that he had a prosthesis. And we ran over, we're like, hey, what happened? What's going on? The day before, he had been fitted for his sort of adult growth custom prosthetic. Up till then, he was just kind of swapping out prosthetics as he kind of grew, right? And they were kind of, not so much a one-size-fits-all, but they certainly weren't tuned to what his condition was. And the reason that they didn't do that is it's expensive to keep making custom prosthetics for somebody that's just constantly growing anyway. But once he got his custom-made, tailored to him prosthetic, the only way you could know that he was wearing a prosthetic limb is if he reached down and took it off during a conversation. He would do that for shock factor. It was actually pretty funny, right? But yeah, because he'd be talking to somebody like new at the school or something, a new teacher didn't know what was going on, right? They'd be talking and he'd just reach down, pluck it off and scratch his head and then put it back on. It was pretty funny. Or if you tried to kick him in the shin, we always told the bullies, hey, go kick him in the shin, and they'd run over, kick him in the shin, and then be on the ground clutching their toes. But the quality of life that comes from tuning a prosthetic to an individual situation comes from our understanding of how the natural pendulums of our body work. And it can lead to a very big quality of life. The Boston Marathon bombing that took place, oh boy, that's quite a while ago now, isn't it? So it's been more than 10, 15 years. This is when a terrorist put a bunch of bombs at the finish line of the Boston Marathon, and as the biggest group of runners was coming through, set them all off, killing people, but also maiming a lot of people. There were a lot of stories of tragedy and triumph that came out of that. One of the stories has always stuck with me, though. One of the runners was simultaneously a ballerina in the Boston Ballet. Timothy Chalamet was young by then. He may not have hated her at that point. The ballerina lost her foot from the ankle down. And was told by her doctors that she would not be able to perform ballet at the same level that she was used to. She'd be able to dance, but being on point, all those other things that ballet dancers do, was not going to be an option. There just wasn't a prosthetic in existence that could articulate enough or support enough of the weight. It would just be too painful, all that kind of stuff. The MIT Robotics and Engineering Department heard about this and decided that no was the incorrect answer. And so over a period of 2 years, they started on a research project and developed a prosthetic limb that had motor servos and things in it that responded to nerve impulses that were still being sent down this ballerina's leg, but weren't connected to anything anymore. And it was one of the first prosthetics that was able to restore perfect function to this dancer's legs, enabling her to continue to dance in the Boston Ballet. That work went on to be put into common everyday prosthetics. motor-driven, servo-driven, machine learning prosthetics where people that have lost the use of their hands can just think. Just like you would think to open and close your fingers. It's just that subconscious, I need to grab something now. Instead of having to like move their shoulder blade to cause the claw to open up and down, using those old neural connections and getting those people quality of life back. The more you understand, the more you are amazed and the more convinced you are that you do in fact live in Star Trek. I'll see you tomorrow for the exam autopsy.